In this lecture, I would like to give an overview of paramagnetic NMR spectroscopy of proteins in solution. Specifically, I will show how to use paramagnetic length-night tags to obtain detailed structural information solely from pseudocontact shifts, that is, changes in chemical shifts generated by the paramagnetism of length-night tags. By structural information, I mean anything ranging from the position of individual atoms, like amide protons, relative to the rest of the protein, to the conformation of polypeptide segments in the protein, but also going as far as determining the entire three-dimensional structure of proteins solely from paramagnetically generated changes in chemical shifts. Paramagnetism causes more effects in the NMR spectrum than just changes in chemical shifts, and each one of these effects presents a way to gain structural information. This lecture aims to explain the origin of these effects in simple physical pictures and illustrate their use with some practical applications, while keeping the eyes open for potential pitfalls and misinterpretations. I was drawn to the field of paramagnetic NMR spectroscopy at a conference over 20 years ago, which was organized by Ivano Bertini and his group in Florence. At the time, they showed that one of the two calcium ions in the small calcium-binding protein calbindin D9K can readily be replaced by a lanthanide ion. Most lanthanide ions are paramagnetic, and the Florence group showed that the paramagnetism produces effects in the protein NMR spectrum that can be observed over a long range, up to 50 angstroms or so. And these effects present powerful structure restraints for assessing and refining 3D protein structures. At the time, I thought, if these paramagnetic effects really are as good as advertised, why not make conventional proteins paramagnetic, simply by attaching a paramagnetic lanthanide complex? As often in research, this deceptively simple idea put my group on a much longer journey than anticipated. Modification of a protein with a paramagnetic lanthanide ion required quite some development. Ultimately, however, it works. With this, let's go. First of all, what is paramagnetism? If we look at a physics textbook, we find the following definition. Paramagnetism is if some usually non-magnetic material becomes magnetic in a magnetic field. Interestingly, the opposite of paramagnetism is not non-magnetic. Instead, the opposite is diamagnetism. Diamagnetism is when some usually non-magnetic material or compound becomes magnetic in a magnetic field, but in an inhomogeneous magnetic field tries to move away from the region of higher magnetic field. Let me illustrate this with an experiment. Here I have a steel surface onto which I am placing 4 magnets. The magnets are oriented in such a way that the north pole of 2 of the magnets points up, while the north pole of the other 2 magnets points down. The result is a highly inhomogeneous magnetic field between the 4 magnets. Then I add a piece of carbon, and magically the carbon floats in the air. The piece of carbon really makes no contact with the magnets, as one can see when moving the magnets a little bit. It appears as if the carbon is trapped in the magnetic fields. How is this possible? We all know that carbon is not magnetic, at least not in the sense that we could possibly make magnets exclusively out of carbon. Yet the force that keeps a piece of carbon suspended in the air is magnetism, diamagnetism to be precise. So the carbon became magnetic in the magnetic field generated by the magnets. And because that magnetic field is inhomogeneous, the diamagnetic carbon is repelled from the regions of higher magnetic field strength, just as prescribed by the definition of diamagnetism. It gets even wilder. In 1997, the European Magnetic Field Laboratory in Nijmegen demonstrated that it is even possible to suspend a frog in a very strong inhomogeneous magnetic field. Here's the link to a YouTube video showing the confused frog. Obviously, Frogs are very different from permanent magnets, but even they become magnetic in a magnetic field because they are diamagnetic. Now, how does this work? What is the underlying mechanism? Think of a magnetic field positioned vertically, then take charged particles, say electrons, and inject into the magnetic field. They will not move on a straight line. They will deviate from the straight line and ultimately move on a circle. And that is also the basis of mass spectrometry, where heavier particles move on larger circles than light particles. Now, in a molecule, the electrons are always on the move in the orbitals that they sit in. If we put the molecules in a magnetic field, the electrons will try to move on circles. Now there is a different system where electrons move on circles, and that is electromagnets. In an electromagnet, we have a coil for which we send current that generates a magnetic field within the coil. So the electrons that move on a circle generate by themselves a magnetic field. And that magnetic field is opposed in direction to the external magnetic field that causes the movement on a circle in the first place. Now, the larger the circle that they describe, the stronger the magnetic moment is that they can generate. Graphene is a very large planar lattice of conjugated double bonds, like fused benzene rings. And their ring currents can describe a very large circle. Hence, there can be a substantial magnetic field generated by the electrons on the circular path. Therefore, a significant magnetic field can be built up, and that is in opposite direction to the external magnetic field that brings about the circular movement of the electrons in the first place. Now, this is a very special situation. In a frog, you wouldn't have large conjugated double bond systems, but the electrons nonetheless can describe small circles. And you have many molecules. If the external magnetic fields are sufficiently strong, the diamagnetic force is also sufficiently strong to sustain the weight of the frog. Now, how is paramagnetism manifested in NMR spectroscopy? First of all, we see line broadening. The paramagnetism arises from unpaired electrons, and oxygen, for example, has 2 unpaired electrons. Now, if you have a sample with oxygen, you observe broader lines, symbolized here by the red line, than in the absence of oxygen. So degassing samples can give you narrow lines, in particular if you have small organic molecules in organic solvent where oxygen dissolves rather readily. This effect is called the paramagnetic relaxation enhancement, or PRE. And if you look at proteins, you can introduce a paramagnetic center intentionally by attaching a stable radical like MTSL. So this has a reactive group, a methane thiosulfonate, that will react with cysteine to form a disulfide bond. And then you have the paramagnetic center caused by the unpaired electron of the nitroxy group. Unpaired electrons have a particularly large magnetic moment. And therefore, what we get with the MTSL label is one large magnetic dipole moment attached to the molecule. The dipole moment generates magnetic field lines. They describe the direction of a magnetic needle in the field of this magnetic dipole. Just above or below the dipole, it would point in the same direction, and along the field lines out here, the needle would point in the opposite direction. Now, these magnetic field lines will interact with the nuclear spins. Let this sphere be a protein, and the red arrow a nuclear spin. We put this protein in a magnetic field, B0, and the field lines from the unpaired electron now will either add to the external field, as they do in this orientation of the molecule, or they will subtract from the magnetic field at the site of the nuclear spin if the molecule is in this orientation, that is 90 degrees rotated relative to the starting orientation that we have on the left. So what we get at the site of the nuclear spin is not only B0, but in addition a magnetic field caused by the unpaired electron. As the molecule tumbles in solution with a rotational correlation time of the order of nanoseconds, the field from the electron spin varies at the site of the nuclear spin. And if the rotational tumbling is just on the right timescale, that is, near the Larmor frequency of the nuclear spin, this oscillating magnetic field can act like a radio frequency pulse at the nuclear spin and drive it back to equilibrium magnetization. So that is a T1 relaxation effect. But more simply, for the different orientations of the molecule, we expect different Larmor frequencies for the nuclear spin. And even though the different situations exchange as the molecule tumbles, this gives rise to line broadening, that is T2 relaxation. The Solomon-Bloembergen-Morgan theory describes quantitatively how much paramagnetic relaxation enhancement we expect. So if we look at R2, the transverse relaxation rate enhancement, we have a constant, we have gamma I, that is the gyromagnetic ratio of the nuclear spin, the G factor of the electron, that is also a constant, µb, the Bohr magnetron, that is a constant, S, the spin of the paramagnetic center, and that is 1/2 for nitroxides, but for a gadolinium ion it would be 7/2. We have a distance between the nuclear spin and the paramagnetic center, and that is a steep distance dependence. It goes with 1/r to the 6th. So if you double the distance, the effect goes down by a factor of 64. And then we have this term that depends on the correlation time, the Larmor frequency of the nuclear spin, the precession frequency of the electron spin. Now tau c is dominated by the smaller one of these two terms, either the rotational correlation time or the electron spin relaxation time. The spin relaxation time for nitroxides and gadolinium ions is of the order of 100 nanoseconds to a microsecond. But for large proteins, also tau r is long. But in the rotation correlation time not only gives the rate with which a molecule tumbles in solution, but it pertains to the vector connecting the paramagnetic center with the nuclear spin. So if a tag that shortens the effective rotational correlation time. So tau c is a bit of an uncertain number, but we can assume that it is fairly long, that for proteins and nitroxides and gadolinium, this is fairly long. And that means that the second and third term in this bracket are very small compared to the first term. So then we end up with this rather simple equation that just depends on the electron spin, the correlation time, and the distance between the electron spin and the nuclear spin. And this in principle can be used as distance restraints. But a complication, of course, arises when the tag molecules are a bit flexible. So the MTSL is attached by a disulfide bond to cysteine. Obviously, these bonds can rotate, and that means that the location of the unpaired electron relative to the protein is a bit uncertain. And that can be presented by a distance distribution. If you look at a particular nuclear spin in the protein and you want to know how much relaxation enhancement does it get from the paramagnetic center, well, we have a bit of a distance distribution. Because the tag is mobile, also the site of the nuclear spin may be a bit mobile. So in this particular example, we have a range between 10 and 30 angstroms. Now, of course, for short distances, the paramagnetic relaxation enhancement is much more effective. And if we multiply this curve by 1/r to the 6th, then we get the blue curve, which just indicates that the short distances contribute a lot more to the paramagnetic relaxation enhancement than the long distances. So what distance restraint do we actually obtain from a mobile tag relative to a nuclear spin that itself may be in a mobile group? And the situation is even more dramatic if you use gadolinium in a tag like this, where the tether between the gadolinium and the disulfide bond that will attach it to a protein is even longer and more flexible. So the distance distribution itself is broad, but when we then also look at the distances that cause the greatest relaxation enhancement, we see that the shift between the two maxima is even greater than in the case of the nitroxide radical, and that is simply due to the longer length of this tether. So the distance restraints that you obtain with paramagnetic tags are not super accurate. There's another way of looking at interactions with paramagnetic relaxation agents, and that is intermolecular PREs. For example, if you take a gadolinium compound like this complex here, it has a certain size, and that means that gadolinium can be positioned at any site that is indicated by a dot here. For a given nuclear spin, we can now calculate how much relaxation enhancement we would expect if gadolinium is uniformly distributed over these dots. Just average all these effects and find out how well it correlates with experimental observation. So the line broadening that was measured experimentally was compared with a calculation, and you see that there is a correlation, but it is modestly good. Even for this particular complex was chosen to be electrostatically neutral. It contains only 3 carboxylates, and 2 of these arms are methyl amides, which are uncharged. So that perfectly compensates the 3 positive charges of the gadolinium ion. So we have talked about the PRE, which is an effect that is essentially just distance dependent. That is an effect that is particularly pronounced for paramagnetic centers that are characterized by long electronic relaxation times. And essentially it is just distance dependent. So if the paramagnetic center is symbolized by the red sphere and the nuclear spin by the yellow sphere, the distance r between the two is what determines the magnitude of the PRE. But what if the paramagnetic center is characterized by electrons that have a short relaxation time, a very short relaxation time, much shorter than the rotational correlation time of the protein? Well, then different equations apply, and we still get a distance dependence, but we also get other effects that are particularly interesting for gaining structural information. First of all, we get so-called pseudo-contact shifts. Now, what that means is that the NMR signal that we observe in the presence of a paramagnetic metal ion with fast electronic relaxation time, and in the following I will only look at lanthanide ions, simply give us different chemical shifts compared to the protein in the absence of the paramagnetic lanthanide ion. And in addition, we will observe residual dipolar couplings and cross-correlated relaxation effects. Now, the chemical shift changes are called pseudo-contact shifts, or PCS. Where does the PCS come from? They are characteristic for lanthanide ions. All lanthanide ions except gadolinium have short electronic relaxation times, much shorter than the rotational correlation time of the protein. And that has consequences. First of all, the unpaired electrons are located in f orbitals, and the f orbitals are not spherically symmetrical. So here's just one example. As the electrons move in orbitals that are not spherically symmetric, they describe circles of different diameter. If the orbital is oriented such that a larger diameter can be described, you get a larger magnetic dipole moment. But if the orbital is directed in a way that only a small circle can be described by the electron, then you get a lesser magnetic moment. And the orientation of the f orbital in a magnetic field, of course, depends on the ligand field of the complex that the lanthanide ion is in. So if you take a protein molecule, and let that be again simply a sphere, and you attach a lanthanide ion, well, it's paramagnetic and it will generate magnetic field lines that can either add to the external magnetic field at the site of the nuclear spin. But now if you rotate the molecule by 90 degrees, magnetic moment of the lanthanide ion may be much smaller because the f orbitals are not differently oriented relative to the external magnetic field. And the magnetic moment of the electron adjusts instantaneously because the T1 relaxation time of the electrons is in the picosecond time range, much faster than the rotation correlation time of a protein. So that then means that in this orientation we observe a large enhancement of the external magnetic field on the nuclear spin, and that is not compensated by a similarly large decrease of the magnetic field when the molecule has reorientated. So then the net effect of all these interactions is that the Larmor frequency of the nuclear spin changes, and that is the pseudo-contact shift. The mathematical description of this is given by the magnetic susceptibility tensor. So what is a magnetic susceptibility tensor? The magnetic susceptibility describes the magnitude of the magnetism of a paramagnetic center. So let this be a lengthenite ion. There will be an axis where the magnetic moment is maximum, and that we call the z-axis. And there will be an orientation where the magnetic moment is minimal, and that we will call the x-axis. And then orthogonal to both the x and the z-axis will be the y-axis. So this object then describes the amount of magnetism that we have at the paramagnetic center depending on its orientation relative to the external magnetic field. So we have three axes that we can call chi x, chi y, chi z. And the pseudo-contact shift that we observe at the site of the nuclear spin I depends on the distance from the paramagnetic center, but also on its position in the coordinate system spanned by the x, y, and z axis of the chi tensor. When one looks at the full equation of the pseudo-contact shift, that is the change in chemical shift measured in ppm in the paramagnetic situation minus the chemical shift in the diamagnetic situation, that is without, say, a lengthenite ion, then it depends on the distance r between the paramagnetic center and the nuclear spin. And it also depends on theta and phi, which are the polar angles describing the location of the nuclear spin in the frame of the magnetic susceptibility tensor. And it depends on delta chi axial and delta chi rhombic. Now, these are defined up here. So we don't need to know chi x, chi y, and chi z, which are three parameters. We only need to know two parameters, which are delta chi axial and delta chi rhombic. So that is describing the anisotropy of the magnetic susceptibility tensor. Namely, the axial component is the long axis, chi z, minus the average of the two shorter axes, chi x and chi y. And the rhombic component is simply the difference between the chi x and chi y. So for an axially symmetric tensor, the rhombic component would be 0, and we would be just left with delta chi axial. So these two parameters can be referred to as defining the magnetic susceptibility anisotropy tensor, or delta chi tensor. If you bind a lengthenite ion complex to a protein, then we also tie a magnetic susceptibility tensor coordinate system to the protein. And for each point in that coordinate system, we can make a prediction of the pseudo-contact shift that a nuclear spin would have if it were at that location. That is shown here. This is nothing else but plotting this equation on a protein structure where a lengthenite ion is bound in the center of this object. This object are so-called PCS isosurfaces, pseudo-contact shift isosurfaces. That is, each nuclear spin located on the surface of this blue object, for example, will experience a certain pseudo-contact shift, say 1 ppm. And if it is located on the surface of this red object, then this would be negative. It would be minus 1 ppm, because this equation can generate both positive and negative numbers. And obviously, the closer you are to the paramagnetic center, the larger the pseudo-contact shifts will be. Conversely, if we know the structure of a molecule and we observe pseudo-contact shifts, we can determine the location of the delta chi tensor, its orientation relative to the protein, and also its magnitude. Now, how many parameters would one have to determine? So how many parameters are needed to determine? So let's assume we know the structure of the protein. How many parameters do we have to determine in order to define the delta chi tensor? We have three coordinates, x, y, and z. We have the orientation of the tensor relative to the protein, and that can be described by three angles, for example, three Euler angles. And we have the axial and rhombic components of the tensor, delta chi axial, delta chi rhombic. So in total, 8 parameters. And that means that if we can determine the pseudo-contact shifts for 8 nuclear spins in the protein, then we can also determine what the delta chi tensor is. In practice, we would use more pseudo-contact shifts than 8, say 20, to have an overdetermined system, and then know the delta chi tensor rather well. In a protein that is 15N labeled, the 15N proton correlation spectrum may look like this. Without a metal ion, that is a diamagnetic protein, we get the black spectrum, and with a metal ion, in this case dysprosium, we obtain the blue spectrum. You can see that the peaks shift along lines that are more or less parallel. And these shifts represent pseudo-contact shifts. They can be to the left, but they can also be to the right. And that is distinguishing positive from negative pseudocontact shifts. The reason why the cross peaks are shifted along more or less parallel lines is that the proton and the 15N are pretty close together, within about 1 angstrom, whereas the paramagnetic center is much further away. So therefore, depending on which orientation the NH bond is, the pseudocontact shift at the site of the nitrogen and at the site of the proton should be very similar. The pseudocontact shift is measured in ppm. And indeed, when you look at, for example, the cross peak of E72, the shift in the proton dimension is something like 0.9 ppm, and in the vertical dimension it also shifts by something like 0.9 ppm. So it is not so difficult to find the paramagnetic peaks that belong to the diamagnetic peaks. We can use different lanthanide ions. And here's an overview of all the paramagnetic ones that one can use. The yellow balls indicate the radius within which the T2 relaxation enhancement would be so severe that the NMR signals would quite likely be broadened beyond detection. So for gadolinium, which has a very long electronic relaxation time, signals within a large radius of the gadolinium will disappear. Whereas for samarium, we may be able to observe nuclear spins that directly contact the metal ion. So here's a scale bar. The scale bar indicates 20 angstroms. When we look at the pseudocontact shifts, gadolinium doesn't generate pseudocontact shifts because its electron relaxation time is so long, but all the other paramagnetic lanthanide ions do generate pseudocontact shifts, terbium in particular, and dysprosium. But interestingly, thulium, for example, generates pseudocontact shifts that tend to have the opposite sign from those of terbium. And that's the reason why we like using both terbium and thulium to measure pseudocontact shifts, because they shift the peaks in opposite directions. Now I should say these particular delta chi tensors were determined by Bertini and co-workers about 20 years ago for a particular protein, calbindin D9K, which is a calcium binding protein where the calcium in one of the binding sites can easily be replaced by a lanthanide ion. If you attach a lanthanide ion by a chemical tag, for example, these isosurfaces can look quite different. But in general, the relative magnitudes reflect the observation made for calbindin D9K, that is, the largest pseudocontact shifts occur for lanthanide ions that are heavier than gadolinium, whereas the lanthanide ions lighter than gadolinium generate more short-range effects. But then also less paramagnetic relaxation enhancement. If you look at a more complicated protein, and this is a 33 kilodalton complex, with diamagnetic yttrium, we obtain the black spectrum, with paramagnetic thulium and terbium, the blue and the red spectra. And you can see that the paramagnetic peaks with thulium are displaced in opposite directions than what we observe with terbium. So in other words, the orientations of the tensors are relatively similar, but the sign of the isosurfaces is reversed. And that helps to identify the paramagnetic peaks that belong to each diamagnetic peak. Having the pair of two paramagnetic spectra helps greatly to assign the paramagnetic spectrum relative to the diamagnetic spectrum. Now, how can we use this in practice? IMP1 is an enzyme that breaks down antibiotics. It has two zinc ions in its active site, and a flap with a tryptophan residue in the mobile flap assumes 3 different conformations in 3 different crystal structures. Now we wanted to know what is the situation in solution. Where is the tryptophan side chain? And for this we can use pseudocontact shifts. We make cysteine mutants of the protein so that we can attach lanthanide ions at position 53, at position 172, and 204. We attach thulium tags or terbium tags, and then measure the pseudocontact shifts in the protein and fit magnetic susceptibility tensors. And the correlation between the experimentally observed pseudocontact shifts and the theoretically back-calculated pseudocontact shifts is rather good, both for thulium, blue points, and terbium, the red points, for all 3 sites. This then gives us the delta chi tensors that determine the pseudocontact shifts at the site of the tryptophan. Here are the three different tensors represented as PCS isosurfaces. And now it's just a matter of measuring the pseudocontact shifts at the site of the tryptophan side chain to find out where it is. For this, to simplify the measurements, we use tryptophan with the carbon-13 labeled indole. So then in a carbon-13 HSQC spectrum, we can selectively observe the proton and its pseudocontact shift that is attached to this carbon-13. For the three sites, the HSQC spectra are shown on the right. Black, we have diamagnetic yttrium tags, red, terbium, blue, thulium. And the site of interest is residue 28. For this particular mutant, for this particular tagging site, we observe large pseudocontact shifts. For the other sites, we observe much smaller pseudocontact shifts. We can also transfer the magnetization by NOE from the CH to the neighboring NH. That's the NOE relayed 13C HSQC spectrum shown on the left. And for the free tags, you can see that the site 28 still generates large pseudocontact shifts. Maybe not quite as large as for the CH. So that says that the NH seems to be closer to the tag at the site 172. And we also see small pseudocontact shifts generated by the other two sites. Now, the intersection of the respective PCS isosurfaces should tell us where these nuclear spins are. And indeed, if you allow for an uncertainty in measurement of 0.03 ppm, then this is where the NH nuclear spin must be, and it corresponds to one of the three crystal structures. For the CH, even if we assume that the error of measurement is smaller, 0.01 ppm, we observe this space indicated by the red dots. We call this space a localization space, the space where the proton must be. Why is this space larger, although the precision with which we have measured is better than for the NH? And the reason is that for the NH, we actually had a fourth set of pseudocontact shifts that we generated with a different tag at the site 172. And that gave a gifted postdoc in my group, Henry Orton, the idea that maybe we don't need to attach the tags at different sites. The tags attached at the same site also provide very valuable information. To investigate this systematically, he considered the following cases. Let the proton be a sphere. Let the nuclear spin be the red dot, and the tagging sites indicated by blue dots. So in this particular model, we have three tagging sites, which we can use to generate pseudocontact shifts at the site of the nuclear spin. They are all equidistant from the site of the nuclear spin by distance d. We make an assumption about the magnitude of the delta chi tensors, but we allow all possible orientations relative to the protein. So for randomized orientations, you may be very unlucky. At the site of the nuclear spin, if the PCS isosurfaces don't intersect at a steep angle, but at a very shallow angle, because we have a certain uncertainty of measurement, the PCS isosurfaces should actually be represented by shells of a certain thickness, defined by the uncertainty of the pseudocontact shift measurement, rather than by simple two-dimensional surfaces. So if two of these shells intersect at a very shallow angle, we'll get a very large localization space where we can't tell where the nuclear spin is with great accuracy. For a systematic investigation, Henry then also considered the situation where we have only two tagging sites, and then there would be opposite on this circle, or even four sites, and they would be equidistant, separated by 90 degrees on this circle, or 5 sites or 6 sites. We also consider the situation of different tags, with the orientation of the delta chi tensors chosen randomly. Then we can calculate the PCS produced by each tensor at the site of interest, which we have marked here by the red point. Of course, very similar PCSs we will predict for the points that are nearby. So which points then do we include in the localization space? So we put the sphere into a grid, and for each point we calculate the agreement between the true PCS that we have calculated exactly for the point of interest, and we consider that to be the experimental PCS, and the PCS that we calculate from our delta chi tensors at each of the points in the grid. The quantitative measure that we choose to measure the agreement between the true PCS and the back-calculated PCS for each point we describe by a root mean square deviation, or RMSD value. So then we assume arbitrarily that we can measure PCS with an accuracy of something like 0.03 ppm, which is a realistic value for the accuracy with which we can measure PCSs in proton NMR spectra. Each point where we calculate a PCS RMSD that is smaller, we include in the localization space. And each point where the RMSD is larger than 0.03 ppm, we exclude from the localization space. And then we ask, how big is the localization space? How well can we determine it by the PCSs that we get from tags located at a variable number of sites? Those sites are marked here by the blue dots. Ultimately, the question is, what are the chances that we obtain a small localization space if we assume different numbers of tags and tagging sites? For each combination of tag numbers and tag sites, Henry did the calculation for 10,000 randomly chosen delta chi tensor orientations, because we don't know those in advance. And that then yields a distribution of localization volumes for each model that we have. So if we have 3 tags at 3 sites, we can get an idea about the chance of obtaining a small localization volume around the site of the red dot. And the result is most surprising. Let's look at the scenario of 4 tags distributed over 4 tagging sites. And that is shown here in red. The vertical axis is the localization volume. The thickness of the line represents the number of times that a certain localization volume was observed. The dot indicates the median of the distribution, that is, 50% of the cases result in a very small localization volume, less than about 1 cubic angstrom. The 95th percentile is marked by a cross. So 95% of the cases result in a localization volume that is smaller than 3 cubic angstroms. Very small. But some outliers went much further. They go to almost 8 cubic angstroms. But in any case, this shows just how well a localization space for a nuclear spin can be defined by pseudocontact shifts. But the really interesting and unintuitive part of this is that the localization volume grows only little if the same number of tags is distributed over 3 or 2 sites. And that is shown by the green or orange data. So even if only a single site is tagged with 4 different tags, that is shown by the blue curve, there is a 95% chance of finding a localization volume that is smaller than 4.5 cubic angstroms. And then if we throw in a 5th or a 6th tag, the median of a localization volume decreases, but only relatively little compared to the situation with 4 tags. So therefore, it is more important to deploy multiple tags than having multiple tagging sites. In fact, the position of a nuclear spin can be defined very accurately by the PCSs generated by multiple different tags attached at a single site. And this is a very important result. Many different lanthanide tags exist, whereas it can be quite tricky to find multiple sites in a protein that are suitable for tagging. Furthermore, little gain is expected from using more than 4 tags. So then, localizing a nuclear spin by PCSs is very different from the global positioning system we use in mobile phones. The GPS approach depends on measuring distances to at least 3 mobile phone towers or satellites. In the case of delta chi tensors, however, we have a different situation. We have non-spherical PCS isosurfaces which contain more information than a pure distance measurement that we use in the GPS system of mobile phones. So then we tested these predictions in practice, and we used the small protein ubiquitin, made a mutant at the site of serine 57, which we mutated to cysteine, And then we tested these 4 different tags, C1, C2, C12, C13. These tags are very similar in chemical structure. C1 and C2 attach via the sulfide bond to the cysteine. C12 and C13 have the nitro group as a leaving group, and that then generates a thioether, and are therefore attached to the protein a bit more rigidly. The C1 and C2 tag are enantiomers of opposite chirality, where the C2 tag has different chirality independence compared to the C1 tag. And the same difference also prevails between the C12 and C13 tag, where the chirality at this carbon independence is different. And we do get different tensors. They're not vastly different, but they're a bit different. And what matters is that they're different in orientation. The C12 and C13 tags produce larger tensors because of lesser mobility of the tether to the protein, so there is less averaging between positive and negative pseudocontact shifts. But on the whole, what matters is that the orientations are different relative to the other tags. Now, the localization spaces that we observe in ubiquitin for the amide protons are shown here by the red dots. And you can see that they very accurately pinpoint the location of the protons in this part of the beta strand, in A as well as in C, whereas in this loop region shown in B, the agreement with the crystal structure is less convincing. And that we attribute to mobility of that loop relative to the protein, which then also is manifested in slightly different PCSs than one would expect in a single crystal, as shown by the X-ray structure. If we wish to furnish proteins with a paramagnetic center using lanthanide ions, we need to have tags that coordinate the lanthanide ion and can be attached site-specifically to a protein. The best tags so far that can bind lanthanide ions very, very tightly are based on daughter. That is a so-called cyclane ring with 4 nitrogens, and the lanthanide ion sits in the center of that ring and is held in place by 4 pentanons with carboxyl groups that provide the countercharges to the positively charged lanthanide ion. And at present, one of the very best tags is this one published by Joss and Heusinger, where the pentant that is used for attachment to the protein is quite rigid. This SO2CH3 group is a leaving group, can be replaced by the sulfur of a cysteine, and as you can see in ubiquitin, the 15N proton HSQC spectrum shows very large PCSs with thulium, these are the peaks in red, or dysprosium, these are the peaks in blue. The actual component of the delta chi tensor for dysprosium is indeed very large, and yet, and still, the quality factor of the fit is a very small number, so it is very good. Now, what is a quality factor? When we fit the delta chi tensor, we try to minimize the cost of the fit, and that is defined by the sum of the squared deviations between back-calculated and experimental pseudocontact shifts divided by the square of the uncertainty with which we measure pseudocontact shifts, and summed over all sites for which we have pseudocontact shifts. The quality factor, however, is given by the square root of the sum of the calculated minus experimental pseudocontact shifts squared divided by the experimental pseudocontact shifts squared. The division by the experimental pseudocontact shifts makes sure that large pseudocontact shifts, which are from nuclei very close to the paramagnetic center, get an inordinate weight in the calculation of the quality factor. The delta chi tensor fit that we use in our program, Paramagpi, however, minimizes a different cost function, which takes the uncertainty of measurement into account. In this sense, the Q factor may be considered to be an independent measure of the agreement between experimental and back-calculated PCSs. Now, most tags are mobile, and that means that the metal ion is in different locations relative to the protein. So here's an example where we simply calculated for a given tag where the metal ion can be when it is attached at a certain site of this particular protein. And you can see that there's a fair distribution. Now, of course, the delta chi tensors for every single point of this distribution. And we don't know how much each of these possible positions is actually populated. Now, does that matter? Does that spoil the whole concept? And the answer is no, it doesn't, so long as you are careful. For example, close to the tagging site, we don't expect to be able to measure pseudocontact shift because we have paramagnetic relaxation enhancements, and the lines are simply too broad to be observed. So what we will observe is pseudocontact shifts at a greater distance. Now, the pseudocontact shifts that we measure allow us to fit one effective delta chi tensor. And that effective delta chi tensor is simply the tensor that gives us a good fit for all the nuclei for which we have PCS and where we know the structure. And so long as we have a site of interest where we would like to determine the structure that is within the range of the fitted data points, then the effective delta chi tensor will give us a rather good prediction of the pseudocontact shift that different conformations would have at the site of interest. And how well does that work? So here's an example. We have a nuclear spin at the site of the red dot, and we have a distribution of possible locations for the lanthanide ion relative to the protein due to a flexible tether to the protein. And we can make an assumption about the magnitude and orientation of the tensor. For each point, we have a model for what the tag structure looks like relative to the protein. We can assume that the delta chi tensor is fixed to the frame of the complex that binds the lanthanide ion. And then we can make an assumption that each point of this distribution is equally populated, and we can average all the pseudocontact shifts generated from these points at the site of the nuclear spin and ask how well does that agree with a single effective delta chi tensor that we have fitted by using the averaged PCS values at that site. And it turns out that if we pick the points where we know the structure and fit the delta chi tensor to those, we can get very good agreement between back-calculated pseudocontact shifts and experimental pseudocontact shifts. And that is shown in this plot. Even though the average delta chi tensor is a fair bit smaller than the delta chi tensor that we associated with the lanthanide complex at each site. Here's an even wilder distribution where the tag can swing around over a great range of angles relative to the nuclear spin, and if we fit a delta chi tensor in that area that includes the site of interest, again we can get a remarkably good agreement between back-calculated and experimental pseudocontact shifts, so long as our delta chi tensor is an effective delta chi tensor simply calculated by fitting the tensors using PCSs of nuclear spins that are in the vicinity of this site of interest. Now, of course, it would be even better if we were to immobilize the lanthanide ion completely. And one way of doing this is by using a non-canonical amino acid, phosphoserine. If we incorporate two of those in neighboring turns of an alpha helix, then a single lanthanide ion can bind to two phosphate groups, and that generates nice pseudocontact shifts and an excellent agreement between experimental and back-calculated pseudocontact shifts. And the other advantage of this approach is that now we have a non-canonical amino acid that we can use to attach a paramagnetic metal ion that is independent of cysteines. So we don't need tags anymore that react with chiral groups of cysteines. Unfortunately, when we tested this with different proteins, we found that the moment that we add lanthanide, there is a high risk that the proteins precipitate. So this is not a universally applicable approach. The jury is still out to find out what is a good tag that one can attach to a non-canonical amino acid. This is still in progress. We have talked about PREs, we have talked about pseudocontact shifts, and there are two more effects that are worth discussing. First of all, the residual dipolar couplings. Residual dipolar couplings manifest themselves in NMR spectra by a change in the splitting that we observe by a change of coupling constants. So if in the diamagnetic state we measure, for example, this coupling constant in the paramagnetic state, we may measure the coupling constant defined by the two red peaks, which is larger. And that splitting is the sum of the scalar coupling constant that was observed in the diamagnetic state and the residual dipolar coupling that occurs in the paramagnetic state. And this coupling depends not on the distance between the nuclear spin and the paramagnetic center, but on the angle that the vector connecting the two coupling nuclei forms relative to the coordinate system defined by the delta chi tensor. That coordinate system also determines the alignment tensor that then determines residual dipolar couplings. Now, how does this work? Residual dipolar couplings are determined by an alignment tensor that is directly proportional to the delta chi tensor. Now, the proportionality constant contains the temperature. The higher the temperature, the less alignment we have. Depends on the Boltzmann constant, which is constant, mu naught is constant, and it depends on the square of the external magnetic field. So at a high magnetic field, we expect a greater alignment tensor for a given delta chi tensor. So what this equation says is that the molecules align in the external magnetic field because they have a delta chi tensor. Some orientations of the molecule are simply preferred because the paramagnetic moment of, say, the lanthanide ion is greater in one direction than it is for another orientation. To visualize how residual dipolar couplings change with splitting, we can use this diagram where we have, say, an NH bond, 15N, nitrogen, 1H proton, and there can be two states for the proton. When we observe the nitrogen, it can be up in the state alpha, and then the field lines go this way around, or it can be in the state beta, pointing down, and the field lines go in the opposite direction. And at the site of the 15N, then these two scenarios give us different effective chemical shifts, if you like, different Larmor frequencies. If a molecule has a preferential orientation in the external magnetic field, also the directions of the NH bonds will assume a preferred orientation relative to the external magnetic field. And that means that we see a shift relative to the diamagnetic situation. Now, if the alignment tensor is proportional to the delta chi tensor, we can measure residual dipolar couplings to obtain the orientation of the delta chi tensor. Here's a typical scenario. We have used pseudo-contact shifts to fit a delta chi tensor. So here's the correlation between back-calculated and experimental pseudo-contact shifts for the alpha protons and the amide protons of ubiquitin tagged with a lanthanide tag that gives a delta chi tensor axial component of -9 times 10 to the -32 cubic meters. And the quality factor is rather good, it's 0.06. Now, when we measure residual dipolar couplings, then we get a correlation that is not quite as good. First of all, if we measure the pseudo-contact shifts in Hertz, they would be larger than the residual dipolar couplings that we measure in the NMR spectrum, so the uncertainty ranges are greater when we measure residual dipolar couplings than when we measure pseudo-contact shifts. When we then fit the alignment tensor and calculate the corresponding delta chi tensor, the axial component is invariably a bit smaller than for the delta chi tensor obtained by fitting pseudo-contact shifts. And the quality factor tends to be worse. And the reason is that we often don't know the orientation of the bonds very accurately, and that is simply because of motions. If a bond wiggles a little bit, that affects the residual dipolar couplings, whereas a small amplitude motion of the bond hardly affects the pseudo-contact shift that we would measure. Therefore, the correlation between experimental and back-calculated pseudo-contact shifts is invariably better than it is when we fit alignment tensors. Outliers are simply residues that assume a different orientation in the magnetic field relative to the structure that we use to fit the alignment tensor. So, pseudo-contact shifts give us great structural information. But to be fair, there are also pitfalls that one has to be careful to avoid. And one is arising from residual anisotropic chemical shifts, abbreviated RAGs. The RAGs effect falsifies PCS measurements by shifting the peaks by a different mechanism, to a small extent. For example, here we have a protein that is tagged with dysprosium, and for a given delta chi tensor, we find that the RAGs effect contributes more than plus minus 0.1 ppm to the observed chemical shift, both for the 15N nucleus as well as for the carbonyl carbon. If you use a paramagnetic metal ion with a smaller delta chi tensor, 27 or -10 times 10 to the -32 cubic meters, then this effect becomes much smaller. So for erbium, the uncertainty due to the RAGs effect in the carbonyl dimension and in the 15N dimension is much smaller. Now, where does this come from? This comes from the chemical shift anisotropy of these nuclei. Carbonyl carbons have large chemical shift anisotropies. 15N nuclei have large chemical shift anisotropies. And the Rex effect can be calculated by this equation that contains the components of the delta chi tensor as well as the components of the CSA tensor and the angles between these axes. And as you can see, it is larger for low temperatures and particularly large for high magnetic fields. For these examples, we have calculated this for measurements on an 800 MHz NMR spectrometer. So what this means is that when we fit delta chi tensors, we like to use only proton pseudocontact shifts and not 15N pseudocontact shifts. Of course, once we have a tensor and we know the structure of the protein, we can predict what the Rex effect would be. And the program Paramagnetic does this for you with default delta chi tensors for nuclei for which reasonable default values of the CSA tensors are available. So this is the main effect to worry about with pseudocontact shift measurements. But also for PREs, there is a caveat for metals that generate pseudocontact shifts. So in those situations, the transverse relaxation rates predicted for a certain position. Here we have an example of GB1 tagged with a particular lanthanide tag, the C3 tag, containing thulium. Now if you look at the predicted PRE, paramagnetic relaxation enhancements, they're plotted on the horizontal axis, we find that the experimental relaxation rates are much greater, and the expected correlation is simply not observed. And why is this? Now, lanthanide ions with fast relaxing electron spins generate paramagnetic relaxation enhancement that are given by the Curie relaxation mechanism. And this is the equation for it. So here we have the Larmor frequency of the nuclear spin, the electron G factor, the Bohr magneton, these are all constants. The electron spin, so for example for dysprosium that would be 7.5, the temperature and the distance between the paramagnetic center and the nuclear spin, which goes again with 1/r to the 6th. And then it depends on the rotational correlation time of the protein. So for large proteins, the second term would be small compared to the first term, and we are just left with a direct proportionality to the rotational correlation time. So this is the theory. But in this particular example, the C3 tag is in the loop region of the protein that is quite mobile. So the tag can be here or anywhere in between, and at each position the lanthanide ion would have a different distance from the nuclear spin where we measure the relaxation rates. In this particular case, if we measure the relaxation rates with a string of 180-degree pulses, so a CPMG sequence, the blue points show the relaxation rate enhancement for the diamagnetic situation. So that is our reference. There is no enhancement, and so we look at the average value, which is 0. But in red is shown the relaxation rate enhancement measured in the paramagnetic protein. And the faster we repeat the 180-degree pulses of the CPMG sequence, the more the paramagnetic relaxation enhancements approach the situation of the diamagnetic case. This is, of course, the signature of chemical exchange of the tag between different positions relative to the protein. One has to be aware that this can spoil PRE measurements. Now, if you look at this equation, you find that the equation is just like CSA relaxation. So we can rename the preceding constant by something that looks like it does in CSA relaxation and call this a delta sigma DSA for dipolar shift anisotropy. So we still have the dependence on the Larmor frequency of the nuclear spin squared, like in CSA relaxation, but a different term in the constant. And this is a useful description because this way one can look for cross correlations between CSA and DSA relaxation. I will come back to this later. For now, let's look at PREs of protons for which CSA relaxation is not so important, and the opportunities coming with measuring PREs using lanthanide ions that produce pseudocontact shifts. So here's an example why this is important for measuring distances from proton PREs. These measurements were done for calbindin D9K, which contains one calcium ion and either one erbium ion in the second calcium binding site, and these are the green points, or a calcium and a terbium ion in the second site, and those are the blue points. So there we have no mobility of the lanthanide ion relative to the protein, because the lanthanide ion sits in the well-defined calcium binding site. Now, if you look at the correlation between predicted and experimental PREs, you find that the erbium data give a better correlation than the terbium data. Or if you were to translate this into distances from the paramagnetic center, you find that the experimental terbium data just give you too short distances, whereas the erbium data are more faithful out to something like 18 angstroms or so. And this is because terbium has a larger delta chi tensor. And with a larger delta chi tensor comes greater alignment of the paramagnetic lanthanide and its surrounding ligand field that is provided by the protein with a magnetic field. So, terbium produces larger RDCs, residual dipolar couplings. Not all of them are resolved, and therefore the NMR signals appear broader than one would expect from paramagnetic relaxation alone. Therefore, PREs can be measured more accurately with a paramagnetic lanthanide ion that produces smaller delta chi tensors. Does this then mean that we should simply not measure PREs with the metal ions that come with non-vanishing delta chi tensors? Well, the truth is that the pseudo-contact shifts produced by these metal ions are actually very helpful for measuring PREs accurately. And the reason for this are intermolecular PREs. Here is an example for intermolecular PREs. Henry Orton made a mixture of two calbindin D9K samples, one containing calbindin with a calcium and a lutetium ion, which is diamagnetic, and the other containing calbindin with a calcium and an erbium ion, which is paramagnetic. Because erbium is paramagnetic, it gives pseudo-contact shifts, and this then allows measuring the relaxation rates of both versions of calbindin simultaneously in the same solution. Both proteins are labeled with 15N, and the transverse relaxation rates of the backbone amide protons were measured. In addition, as a reference, the relaxation rates were measured for a sample of purely diamagnetic calbindin, that is, the version containing a calcium and a lutetium ion. Here is what we observed. The plot shows the difference in relaxation rate observed for the diamagnetic protein, namely the protein with lutetium, when measured in the presence and absence of the protein containing erbium. So this measures the intermolecular relaxation arising from the presence of the erbium protein. And although calbindin D9K is a very soluble and perfectly monomeric protein, the effect is significant. In particular, in the region around residue 50, the intermolecular PRE is substantial. When we plot this on the structure of calbindin, here the calcium ion is in pink and the lanthanide ion is yellow, we see that the intermolecular PRE is not limited to a single region of the protein. So the PRE is symbolized by blue spheres with large radius for large PREs, smaller radius for smaller PREs. This should be a bit of an eye-opener. If I take a protein with a nitroxide tag to measure PREs, I have simply no way of verifying that all effects are intramolecular. I can try diluting the protein to reduce the chances of intermolecular PREs, but this can be done only up to a point, because once I have diluted, say, tenfold, the signal-to-noise ratio is so miserable that it's difficult to measure relaxation rates, especially of broad signals. Dilution simply does not make a great controlled experiment. This then means, therefore, that relaxation rates are actually best measured for mixtures of paramagnetic and diamagnetic protein. And in order to gain independent access to both, paramagnetic protein must show different chemical shifts, that is, pseudo-contact shifts. And erbium does this very well. Here's the recipe that I recommend. Use erbium. Use short relaxation delays to minimize the influence of residual dipolar couplings. Shorter than 10 milliseconds will do. Use a relatively low magnetic field strength, say 600 MHz, rather than a higher field, to minimize residual dipolar couplings. Of course, The spectrum of a mixture of diamagnetic and paramagnetic protein will have twice as many peaks. For double-labeled protein, this can be addressed by measuring the relaxation rates in a 3D HNCO spectrum rather than a 2D 15N HSQC spectrum. As shown in these plots, comparing experimental and predicted PREs or experimental distances from the erbium ion versus the distances observed in the crystal structure. This way one can get remarkably good correlations, out to well over 20 angstroms, where the PREs are already quite small. Disentangling intramolecular PREs from intermolecular PREs is one thing. Using the right nucleus is another. Measuring PREs of protons, as we have done here, is usually quite safe. In contrast, there can be pitfalls when measuring PREs of nuclear spins with large CSA tensors, such as 15N or carbonyl carbons. Here is what happens if one has nuclear spins with large CSA tensors and measures PREs with a lanthanide ion that comes with a non-vanishing delta chi tensor. In this case, the previously mentioned cross-correlation between CSA and DSA becomes relevant. Now, how does this work? Let's look at the example of a nuclear spin N in the magnetic dipolar field of a metal M. At the site of the nucleus, this dipolar field can be represented by a dipolar shift tensor, or DS tensor. The red lobes indicate an increase in the overall magnetic field strength, but when we rotate the molecule by 90 degrees, the blue lobes align with the external magnetic field, assumed to be pointing up, indicating that the overall field at the site of the nuclear spin is decreased. The dipolar shift tensor can be decomposed into an isotropic component that produces the observed change in chemical shift, that is, the pseudo-contact shift, and an anisotropic component that drives relaxation but causes no net change in chemical shift. The DSA tensor is of a shape just like a CSA tensor. If both happen to align, two things can happen. They either interfere constructively or they subtract from each other, leaving only a small net anisotropy tensor behind. If they add constructively, the nuclear relaxation will be enhanced. If not, the CSA relaxation observed in the absence of the paramagnetic metal ion will be attenuated in the presence of the paramagnetic metal ion. In other words, the nuclear relaxation can be slower in the paramagnetic molecule than in the diamagnetic reference. This means that a PRE can be negative. The equations shown here give the equations for the DSA relaxation rates R1, longitudinal, and R2, transverse, in a form that highlights their similarity to the common equations of CSA relaxation. Of course, DSA relaxation is nothing else but another name for Curie spin relaxation. That nuclear relaxation can be slower in the paramagnetic than in the diamagnetic state has been demonstrated experimentally, both for the T1 and T2 relaxation rates, using 15N relaxation of calbinium D9K loaded with either thulium or terbium. Here are the data for the T1 relaxation rates. If we consider only DSA relaxation, no negative relaxation rates can be predicted. By taking into account that the nitrogens of backbone amides have sizable CSA tensors, we get a much better correlation between experimental and predicted PREs. And indeed, there are examples where the nuclear relaxation proved to be slower in the protein containing a paramagnetic lanthanide ion than in the protein loaded with diamagnetic yttrium. The last paramagnetic effect I wish to discuss is cross-correlated relaxation between DSA relaxation and dipole-dipole relaxation. This effect is completely analogous to the cross-correlation between CSA relaxation and dipolar relaxation, which leads to different line widths of the individual components of a doublet. Famously, Drosy measurements rely on the effect by selecting the narrow doublet component. The additional presence of a DSA tensor can either enhance or attenuate the imbalance between the two doublet components. Measuring the DSA dipolar cross-correlation effect relies on the same protocol as the measurement of all other paramagnetic effects. The relaxation rates of the two doublet components are measured in the presence of the paramagnetic metal ion, and the corresponding relaxation rates in the diamagnetic state are subtracted. For a pictorial representation of the DSA dipolar cross-correlation, let's consider the proton NMR spectrum of a proton spin bonded to a 15N spin. Depending on the orientation of the NH bond in the magnet, the dipolar field lines of the nitrogen can, at the site of a proton, either add a small magnetic field to the external magnetic field, as shown on the left by the green lines, or subtract it, as shown on the right, for the situation where the nitrogen spin is in the other spin state. If we rotate the molecule by 90 degrees, the situation changes sign. That is, the nitrogen in the spin state shown on the left decreases the overall magnetic field at the site of the proton, whereas it increases the field in the spin state shown on the right. In addition, the proton is exposed to a DSA tensor produced by the paramagnetic metal ion. The orientation of the DSA tensor depends on the delta chi tensor of the metal and on the location of the metal relative to the proton. In the orientation shown here on the left, the net effect of the DSA tensor, symbolized by the white arrow, aligns with the green arrow that describes the effect of the dipolar field due to the nitrogen. In the other spin state of the nitrogen, here on the right, the two arrows point in opposite direction, cancelling the contribution to relaxation. Therefore, the doublet component on the right is narrower than the doublet component on the left. All this is just like in the familiar case of CSA dipolar cross-correlation, except that the DSA tensor can be in any orientation relative to the NH bond, whereas the CSA tensors tend to align with the NH bond quite closely. In summary, the DSA dipolar cross-correlation effect depends on the angle delta between the line connecting the proton spin I with the metal ion and the bond connecting the proton with the coupling partner, for example nitrogen, here referred to as spin K. It also depends on the magnitude of the DSA tensor and therefore on the distance r between the proton and the paramagnetic center. The equation describes how the difference in relaxation rates of the doublet components depends on angle, distance, and rotational correlation time. In order to fit delta chi tensors to protein structures using paramagnetic effects, such as PCSs, Henry Orton wrote the Python program Paramagpy that provides a convenient interface and accepts all four different types of paramagnetic effects discussed. These are PCSs, RDCs, PREs, and DSA dipolar cross-correlated relaxation. The program can handle the simultaneous input of data obtained with different lanthanide ions, allowing the use of a common metal position in the fit. It accepts the PDB format of crystal structures as well as NMR structures, which contain multiple conformations. It can be used to determine uncertainties. It plots correlations between experimental and back-calculated data. It applies Rax corrections if desired. If there's anything that exceeds the interface, for example, data from more than 6 different lanthanide ions, the program also offers a scripting option that is independent of the graphical user interface and can handle such less common demands. Conveniently, the definitions of Euler angles and units are consistent between fits of alignment and delta chi tensors. And to date, we have not found any error in this software. The program was published in the first issue of Magnetic Resonance in 2020. Finally, let me advertise Magnetic Resonance. This is a recent journal founded to address the business model of established publishing companies who extract astonishing profits on the back of publicly funded research. This journal is different. It is owned by Society, the Groupement Ampere, and published by Copernicus Publications, which is a small not-for-profit publisher in Göttingen, founded over 20 years ago by an initiative from the Max Planck Institute. It is an open access journal which publishes the submitted preprint right away, makes referee reports public, anonymous if a reviewer wishes, welcomes comments from the NMR community during the review phase of the preprint, and finally publishes the carefully typeset final version of the article in the journal proper once the reviewer's comments have been taken into account. Magnetic Resonance is a quality journal indexed in PubMed. It accepts manuscripts in LaTeX and Word format, and its open access charges are much more benign than those of established journals. Have a look and perhaps submit an article.